Hello, so this is fractional distillation of crude oil. Before I can talk about that though, I just need to go for a little bit of theory about what a liquid is and what a gas is, which may seem basic but it's really relevant to this explanation. So if I have a liquid, what we have is our atoms or our molecules, and what they are is they're joined together by intermolecular forces. So that's what stops the atoms from just flying away into outer space. We've got these intermolecular forces joining them all together. Now if I heat that up and I change this liquid into a gas, what actually happens is we break the intermolecular forces and the atoms are free to whiz off as they like, and they're now a gas. So basically, the only difference between a liquid and a gas, 2 seconds, I'm just going to go shut the door. Only difference between a liquid and a gas is liquid still has its intermolecular forces, whereas in a gas, the intermolecular forces have been broken. So if I have very, very strong intermolecular forces, it will be harder to change it into a gas. It'll be easier for it to be a liquid, because it needs more energy to break these forces. Okay? So the stronger the intermolecular forces, the easier it is to change it into a liquid. You need to bear that in mind for this next explanation. Okay, so crude oil. What is crude oil? Crude oil is lots and lots of different sized hydrocarbons. So if I had a big pot of crude oil, I'd have some very, very long chains, maybe 50, 60 carbons long, a few medium chains, 20, 30 carbons long, a few short chains, 6 or 7 carbons long, and a few, and a few very short carbon chains, maybe 1 or 2 carbons long. So it's a big, big mixture, it's kind of a mess. And you can kind of think of crude oil as Viagra for the Pope. Expensive, but essentially useless. It's a big, thick, gloopy mess. It doesn't really do anything, doesn't have nice properties, we can't really use it for much. So what we have to do to it is separate out all these different lengths into vats of the same length. So we need to separate out the big ones, stick it in one vat. We need to separate out the middle ones, stick it in another vat, and so on and so on. Basically, we're going to separate crude oil according to chain length. Okay? And here's how we do it. We use something called a fractionating column, and it's basically a huge, huge column, like 3 times the size of a double-story house, and it basically just looks like this. And every now and again, it's got an exit hole at different heights of the column. And what we do is we get our crude oil. Shut the door, please. Close the door, run, go. Close the door and go. Thank you. What we do is we get our crude oil and we stick it through a huge heater. And this heater is really, really hot. And what happens is it evaporates all the oil. It changes all the oil into a gas. We then feed the oil into our fractionating column. And what do hot gases do? Well, hot air rises. So all these hot gases are going to rise up the fractionating column. But what we also do is we heat the fractionating column from the bottom. Okay? So the temperature at the bottom is very, very high. But if I had a Bunsen burner on the floor and I put my hand on it and it wasn't so incredibly hard, I would probably scream. But if I lifted my hand up to like up here, I'd be fine. Because as we get higher and higher, the temperature gets lower and lower. And the same is true for a fractional distillation column. It's very high at the bottom, the temperature is medium in the middle, and it's actually about room temperature at the top. So as we go up, the temperature decreases. Okay? Now here's where we need to think back to what I said at the start of this clip. The size of the intermolecular force determines how easily it changes into a liquid. The higher the force, or the stronger the force, the easier it changes into a liquid. Now let's look at different size carbon chains, and I'm just going to use 2 examples. A short chain, 2 carbons long, and a long chain, 4 carbons long. Now, if I have 2 short chains, like that, they're going to only have 2 sets of van der Waals forces between them because of their carbon's electrons. So that's not very many intermolecular forces. So it's going to be very hard for those to change into a liquid. Whereas for the longer chain, because they've got much more van der Waals forces, or intermolecular forces, they've got 4 sets of van der Waals forces. Their intermolecular forces are going to be a lot stronger, so they can change into a liquid at a higher temperature. So your long chains like this one will actually come out here at the bottom. They will condense into a liquid at the bottom of the fractionating column. So we'll end up with long chains leaving here. Because they've got more van der Waals forces, they can change into a liquid at a higher temperature. And all the shorter chains, they stay as a gas and they rise up. Now when our middle length chains get to here, because it's a lower temperature, they can condense into a liquid. And when they do, they funnel off in here. So we get our medium chains leave at this level. The very, very short chains, because they've got hardly any intermolecular forces, they keep on rising right to the top, and they'll leave somewhere around here when they condense into a liquid. And your shortest of shortest chains, your methane and your ethane and that kind of stuff, they stay as a gas and they raise right to the top and they pump out as a gas at the very top. So your very short chains leave here. So what we've done is we've separated out our crude oil mixture into different what we call fractions. So each of these is a fraction, and each fraction contains a different length hydrocarbon. Now what they're going to want you to say in an exam is that we have separated out the hydrocarbon chains according to their boiling point. So that if you have a mark scheme, that's what it would say in the mark scheme. Separated out according to boiling point. Okay, and that's fractional distillation. Sorry about all the interruptions.